Hi, and welcome to the Neurological Foundation's Discovery Sessions. The Neurological Foundation has been funding research into neurological conditions and disease for nearly 50 years. We have funded some amazing scientists and clinicians throughout their career who have gone on to conduct groundbreaking work and discover fascinating things about the human brain. We hope that these digital discovery sessions will help all our followers, supporters, and fellow science enthusiasts learn new things about one of the most complex organs humans have, their brain. Today's speaker is Dr. Joon Kim, a research fellow at the Department of Physiology at the University of Otago, working in Dr. Carl Eiermonger's lab. In 2020, he received the Brain Health Research Center's Emerging Research Award on his work he is currently conducting on stress in the brain. Dr. Kim's work specifically looks at understanding how neural and behavioral responses to stress are regulated. We are grateful to Joon for taking time today to speak to us about his unique work he is currently conducting on stress in the brain and helping us understand our fight or flight responses better.
Hello everyone, and thank you for tuning in. I'm going to start by saying something that you all know to be true. So a little bit of stress can be good, but too much is unhealthy. And I'm sure that many of us can also distinguish when stress is becoming unhealthy. But why and how do the good effects of stress start to turn bad? To answer this, we first have to understand what stress is doing to the brain, specifically what happens in the brain during stress, and how does the brain deal with stress in order to prevent bad stress. The origin of our stress response is for survival. In situations such as coming face to face with a predator, the stress centers in our brain become immediately activated, and this leads to a burst of energy being released from the body and also boosts our brain function. Everything we need to try and escape from such a dangerous situation. Besides survival needs, many of our daily tasks, activities, or even hobbies can also activate our stress response, such as exercise or competitive sports, even public speaking, or simply doing work that requires extra attention and focus. In such cases, stress has a positive effect and helps us throughout the day, providing bursts of energy and focus when we need it. Unfortunately, stress can start to have negative consequences if it is continuous or long-lasting. Stress in the form of anxiety, fears, grief, financial insecurities, or being overworked can cause long-lasting or chronic activation of our stress response day in and day out. And the build-up from all this stress can cause us to get stressed out. The brain's main mechanism for dealing with stress is called the hypothalamus pituitary adrenal axis, or simply the HPA axis. This involves interactions between the brain and the rest of the body to control our reactions to stress. And the master controller of the HPA axis is the brain, specifically within a small part of the brain called the hypothalamus. And within the hypothalamus lies a specialized population of neurons that responds to stress called CRH neurons, which stands for Corticotropin-releasing hormone. CRH neurons are activated by stress and communicate with various different brain regions to regulate fear, anxiety, and the fight-flight response. They also release their contents into a blood vessel, and they use this to send their message to the rest of the body. And through a series of reactions, this leads to the release of the stress hormone cortisol from our adrenal glands. So CRH neurons play the role of a conductor to orchestrate the stress response both in the brain and the rest of the body. Once cortisol is released from the adrenal glands, it travels all over the body and it has many positive effects like boosting energy and cognitive function. These short bursts of cortisol release is good for us. In fact, every morning when you wake up, this HPA axis is activated whether you know it or not, and it helps us kick into gear and start the day. But when stress becomes too much or it's continuous, you consequently get too much CRH neuron activity. And this leads to high, excessive levels of cortisol over a long time. And what happens is the mechanisms that normally drive the positive effects of stress start to become exhausted and used up, and the bad effects of stress start to emerge, such as changes to our energy balance, leading to metabolic disruptions. And the brain itself begins to deteriorate. It loses its synaptic connections and literally shrinks in size. Too much stress is also a major contributing factor that leads to a number of mental health illnesses. In fact, one of the most well-recognized findings in patients with anxiety or depression is elevated cortisol. So it's critical that the activity of the CRH neurons are kept in check to prevent too much activation. And this is the focus of my work. My research is designed to understand how CRH neurons respond and deal with stress. And I do this by looking directly at their neural activity. Truth is, over decades of work, numerous different research labs from all over the world have studied CRH neurons. And through all this past work, we actually have a really good understanding of CRH neurons. If I use a car as an analogy, essentially we know all the bits and bobs inside CRH neurons that makes it tick. And yet, until very recently, we had yet to answer a remarkably simple question, and that is, what do CRH neurons do during stress? Now, this might sound a little bit confusing given that A, I've told you CRH neurons are activated by stress, and B, it seems like we already know all there is to know. But even though we know all the parts and machinery of CRH neurons, we have yet to scratch the surface when it comes to understanding or even observing how CRH neurons work in a running and functioning brain. Everything we know or think we know about CRH neurons comes from either measurements from blood, which is used to estimate what CRH neurons might be doing, or through studying brain tissue post-mortem. While these are incredibly useful, they are essentially just snippets of the big picture and give us a limited view of how everything actually works together. And that is essential for us to understand how and when things go wrong. But with neuroscience research, you can't just pop open the hood and see what's going on in the brain, which is why we do experiments on animals, and in my work, mice. In order to understand what CRH neurons are doing in a running and functioning brain, well, we need to look at brains. And over the last few years, technology has advanced so much and opened new windows for us scientists to address questions that could not be possible before. Let me show you one example. What you're seeing in this video is an entire brain inside a living juvenile fish. They have a transparent outer body, sort of like whitebait. So you can actually look through into the brain using a specialized microscope. The flashing dots that you see are individual neurons or brain cells being active at the very moment that they flash. These neurons are genetically engineered in a way that causes them to flash light whenever they emit their electrical signal. These light flashes are nowhere near visible to the human eye, and to see them, we need a super sensitive photo detector. So with this technique, we can essentially look under the hood and see what's going on. It's remarkable, I think, to think about how everything that's going through this fish's mind is encoded by these flashes of light. This is a technique that I have adopted for my research, specifically looking at the light that is coming from CRH neurons. So here we have a piece of brain tissue that is kept alive in an artificial setting. And we've genetically engineered only the CRH neurons to have this feature where they emit this tiny, tiny amount of light whenever they are active. If I measured the amount of light over time, it looks a little bit like this, where the upward peaks represent increases in light and therefore more neural activity. Although mice or any mammal that I'm aware of don't have a transparent outer body, we can still detect the amount of light that's inside the brain, giving us a direct look into the CRH neuron activity within the functioning brain. So using this technique, we can begin to really address the burning questions like, how does the brain deal with stress? Now, there are actually a number of different ways that the brain can deal with stress. I will talk about one of them today, which is called habituation. Habituation is essentially a learning process or adaptation that allows us to overcome our fears and find things less stressful over time. This happens through the CRH neurons retuning or recalibrating their activity to prevent excessive stress. A great example of habituation can be seen within individuals that are asked to speak in front of an audience. Studies show that if you recruit healthy volunteers to give a public talk, their cortisol levels become elevated due to stress. But if you ask those same individuals to give a public talk 4 days in a row, by the 4th day, they barely have any cortisol. So by adapting and learning, the HPA axis can change the way it behaves to prevent excessive stress. This is probably because CRH neurons themselves have changed their activity, but as I mentioned, we simply don't know what's going on inside the brain during this process. So we turn to our animal model. Unfortunately, mice won't understand the concept of a public talk. So instead, we exposed them to an alternative but still very mild stress by playing a white noise for 5 minutes. This sounds like radio static, and it's about as loud as someone vacuuming the house. And although this noise is harmless, the mouse will perceive it as a potential sign of danger. And now, by recording the light that's coming from our genetically engineered CRH neurons, we are able to see just how CRH neurons deal with stress inside a running and functioning brain as it happens in real time. So here is a small taste of the data that I work with. What you're seeing in the red line is the amount of light that is coming from the CRH neurons as a mouse experiences this noise. You can see that when the noise is being played, as shown by that square box, the amount of light that is detected is increased. This is because the CRH neurons are activated at that moment. And then when the noise goes away, the CRH neurons gradually turn off. Much like the 4 days of public speaking in humans, if mice are exposed to this noise once a day for 4 days, we can see this habituation process taking shape in their CRH neurons as they happen. And so by the 4th day, there is hardly any activity coming from the CRH neurons as opposed to day 1. This is a positive change. It's essentially our built-in safety mechanism that allows the brain and therefore the rest of the body to deal with stress by preventing excessive stress responses. And our lab was the first in the world to discover that CRH neurons are indeed capable of adapting their activity and by applying this cutting-edge technique. Unfortunately, this process of habituation doesn't always happen to everyone or during situations of chronic stress. So the million-dollar question remains, that is, how do we deal with stress when it becomes a bad stress? One simple answer might be to just turn off the CRH neurons in the brain. But then if we did that, we would also lose the positive effects of stress, which we need. So instead of turning off CRH neurons, I believe that the key lies in understanding the mechanism in the brain that mediates these positive changes. So the question in my mind is, how did the CRH neurons in these mice change their activity, adapt, and become resilient to stress? This is a major question that we are trying to address now, and this involves looking not only at the CRH neurons, but also other neurons in the brain that communicate with CRH neurons. We call this a circuit. Such a circuit would work to coordinate and determine how much activity the CRH neurons should engage in. And so I believe that it's possible we could one day hijack this pathway or circuit and push the brain into self-healing when a stress becomes harmful. These types of research were only made possible in recent years. We now have essentially a toolbox of optical techniques that allows us to look under the hood of the black box that is the brain. And I believe that technological advances will continue to provide new windows and insights across all of neuroscience. And with that, I'd like to thank everyone for their attention, and I thank the Neurological Foundation for their support and the opportunity to speak to you today. Thank you. So first question, why is it just fight or flight and not fight, flight, or freeze? So I'm assuming the question is, why don't we just freeze in certain dangerous situations? And the answer is that we do, but generally such behaviors don't lead to as much favorable outcomes. And so we generally tend to have both happening at the same time. It's essentially our decision whether we freeze or we choose to flee, if I'm interpreting that question correctly. Question 2, where do you hope to go next with your research? I've shown you today about how we've recorded the CRH neurons. The next one is to look at CRH neurons and the circuit at the same time, not just recording it, but also being able to manipulate and alter the communication in this pathway to see how that affects the stress response. Question 3, do you have some examples of interrupting the circuit that have been successful? Not at the moment. So such circuit research actually requires what you may call a double transgenics. So we have such a thing called a Cree mouse that allows us to genetically engineer whatever neurons we want. And we need a second one, and we call this now most commonly as a flip mouse. And so we have just got these technology in where we can alter two distinct populations and be able to interrupt the circuit while recording CRH neurons. And so we will be doing that very shortly. Initial observations, initial testing is underway. Question 4, what is the biggest challenge your research faces? It's a lot of trial and error and a lot of technique development that went into it, and many hours of pulling your hair. So those were the main difficulties. Question 5, how can we self-heal the brain? That's a good question. So we know that the brain is plastic, and which is why it can go bad and it can also go well. And self-healing is one way to describe it. What I generally meant was that if we could learn the process of how the brain rewires or changes in a positive way, we could try to adapt or take that into our everyday lives and essentially make positive changes to our behavior and therefore allow that to self-heal, if that makes sense. Question 6, what are your thoughts on a regular mindfulness practice to help? I think it's absolutely important for us to every now and then take a step back and do things that are mindful. It could be something even as simple as deep breathing for a little bit, or even going for a hike. These things have very positive effects on the mind, even though hiking may be a little bit, may cause a slight stress response by itself, but it's more about how it's affecting our mind that is just as important. Question 7. What meds are currently used for issues related to CRH? So the issues we currently have with CRH are not being used. The medicines we have for it, we can either block CRH or we can block the downstream hormones like cortisol. Those treatments are available, however, they're not being used for mental health illnesses for obvious reasons. Like I mentioned, we actually need CRH and cortisol for everyday life. Question 8, you said that the bad effects of cortisol was loss of brain connections and shrinkage of the brain. Would you be able to elaborate on the extent of this? So the main area of the brain that suffers from this loss of connections or synapses happens in the hippocampus, which is part of the brain that's important for memory. And the shrinkage of the brain is a very, very small effect that happens very gradually. It's just one way to describe the impact that stress can have on the brain. But there are parts of the brain where, especially in those regions that are involved in fear, where connections can go up, and so your fear sensitivity also goes up with it. Question 9, were there any other physical factors that contribute to the mice experiments' RE habituation, like epigenetic generational markers being taken into account with the mice used in the experiment? So if one physical factor that we were concerned about might be desensitization to sound by itself. So the noise is actually about as loud as a handheld drill. So it shouldn't be enough, or at least it's been tested, that it's not enough to cause physical hearing damages. And we haven't looked at epigenetic generational markers. These mice are not used subsequently for breeding. Question 10, does brain shrinkage reverse? Yes. Question 11, what are the suspected or hypothesized side effects of interrupting the circuit? Well, we're not actually looking for this as a treatment avenue. I believe, we look at this as a way to understand what the circuit is and what it does. So we can start to identify other brain regions that are culprits, essentially. But if such treatment options do become a reality in humans, I suspect there would be, in order to prevent some of the very negative side effects I can think of, it would have to be applied in a very controlled, specific timing and environment-based way. Question 12, does brain shrinkage carry on if the stress has reduced? It'll eventually come back as eventually the level of cortisol drop back down and it stays down for a little bit. What you'll have is homeostasis, and things generally will come back to normal slowly but gradually. Great. So I think that's all we have time for today. Thank you very much for tuning in and putting up with me. Cheers.